So what we are going to do today, we will start with the same point where we left, that we have a two-stage amplifier as shown here, which we normally call it as a workhorse for us. So a two-stage amplifier for us. Okay. So two-stage operation amplifier, and we put some specifications so that we can design this two-stage amplifier to achieve or to meet those specifications. And main thing, that what is meant by the design, which we also clarified in the last lecture. By design, I mean we need W by L of this M3, W by L of this M4, M1, M2, M8, M5, M7, M6, all of these width and length of transistors, and also the value of this capacitor Cc, and this I ref current, what is the current flowing through this I naught, and the same thing, what is the current going to flow from this node. So all of these currents, for example, this is I5, this is I6, whatever the currents flowing through these transistors, we also want to know these values. And the specifications we placed in last time, where we have a gain value of 100,000, meaning 60 dB, a gain bandwidth of 30 megahertz, we supply voltage of 1.8 volts, slew rate of 20 volts per microsecond, common input common mode range going from 1.6 to zero point 0.8 volts, load capacitor of 2 picofarad, phase margin of 60 degree, and power consumption of 300 microwatt. We also mentioned about common mode rejection ratio, power supply rejection ratio, noise, but as we mentioned that we will not use them in the design at this moment, but if you want, you can also place them and you can just figure it out whether you are meeting those requirements or not. So let's start with the design, continue from the same point where we left in the last lecture. So just writing again the overall transfer function of two-stage amplifier. So as we concluded that we're going to have some a DC gain K multiplied by some a zero. That zero was coming because of that compensation capacitor. So that zero is going to become dominant, and that, just to clarify, this zero is a right hand plane zero. So its impact is going to be same as a zero for the magnitude, but in terms of phase, its response is going to be similar to the pole. That we need to make sure this thing. And then we have a dominant pole named as omega p1 and a non-dominant pole as omega p2, which is a parasitic pole. So the K gain value, which we derived in a couple of last lectures, that gm1 times R02 in parallel with R04 times gm6 in parallel multiplied by parallel combination of R06 and R07. The zero, as mentioned, it's a right hand plane, so it's going to be minus gm6 by cc. Omega p1 is 1 over R02 in parallel with R04 times gm6, R06 in parallel with R07 times cc. This value was after the addition of compensation capacitor. Omega p2 after the addition of compensation capacitor move more towards the right hand side, so it becomes gm6 by cgs6 by cl, and the unity gain or the gain crossover frequency was gm1 by cc. We did this all the things, and if we want to see a pictorial representation, we have this one representation. And for this design, we are taking one assumption, and this assumption is going to be utilized in our analysis, that omega z is pretty much bigger than omega naught. Why? So that its impact is not going to disturb the phase margin, or it's not going to impact this omega naught. So that's why we are assuming, or we are considering omega z is going to be very much bigger than omega naught, and in order to nullify the effect, 10 times factor is sufficient for us. So we are assuming, or we are considering omega z is equal to 10 times omega naught. So after that, last time we started with the phase margin and the slew rate. So just repeat the phase margin just to ensure nothing is missing, that we have a phase margin of 60 degree. So we know the CL. So first what we are going to do, we will find the CC. So in order to find CC, we are going to put the phase margin equation, that phase margin PM is equal to the phase of a system at gain crossover frequency, meaning omega naught at this point, plus 180 degree. Let me use a different marker, identify the variation. So phase margin is 60 degree, we are placing minus tan inverse omega by omega p1 minus tan inverse omega naught by omega p2, and because of negative 0 or a right hand plane 0, we are writing minus tan inverse omega by omega naught by omega z, and then the plus 180 degree is going to come. We know that omega p1 is the dominant frequency. This means it's going to come way earlier than omega naught. So we can safely say that minus tan inverse omega naught by omega p1 will be equivalent to 90 degree, rather minus 90. So minus minus. So it's going to be ultimately 90 degree. Minus tan inverse omega naught omega p2, let's write as it is here. And this omega naught by omega z can be replaced by omega naught by 10 times of omega naught. We just did the sign inversion here, so that now we have 180 minus 60 120 here, and all the signs are positive on this side. So 90 degree plus tan inverse omega naught by omega p2 plus tan inverse 1 over 10. So if we want to replace tan inverse 1 over 10, it's going to be tan inverse 1.1, which is equivalent to 5.7 degree. And here 120 minus 90 is going to be 30 degree. Going further, if we just take this 5.7 on this side, it's going to be 24.3 degree, equal to tan inverse omega naught by omega p2. Coming back, taking the tan on both sides, we will be left with omega naught by omega p2 equal to 0.4515. So this is the important factor, one of the first design equation which we found from the specifications provided to us, and that specifications were basically related to the phase margin. So what we are going to do, that last time we said, okay, now we know that what is the relation of omega naught and omega p2. So we replace omega naught by gm1 by cc, which we derived in our analysis, and the omega p2 was equal to gm6 by cl. In reality, it was coming as gm6 by cl plus cgs6, but cgs6 value will be relatively less than cl, so we can approximate it to gm6 by cl. And then taking an assumption, we want a higher gain, so gm1 is equal to gm6. If you want any other assumption, then later on your values are going to change accordingly, but at this moment we are considering gm1 is equal to gm6. When gm1 is equal to gm6, we can place in the previous design equation of omega naught by omega p2 of 0.4515. This will conclude that cc will be equal to 2.2 times cl. So that is the first value or which is required for our two-stage amplifier, and that is the cc value. So we know already cl provided as a design specification, which was 2 picofarad multiplied by 2.2, it will be 4.4 picofarad. As a design, we have margin all the time, and we have to pick the reasonable practical value. So 4.4 might not be that much good, so we will go for a 5 picofarad value, which is relatively available. So we can go for a cc as a point at a 5 picofarad, and that's a reasonable value. Picofarad mean exponential 12 minus 12, so it's something which we can integrate on chip. That is basically the value of the capacitor we are going to use. So this value of the capacitor we are going to use in the next analysis. So since we got this value, we can write that, okay, in this two stage we got this cc as a 5 picofarad. So I will continue writing as we get the value. So we got this cc as 5 picofarad. And let me write the cl also. We have a cl equal to 2. So coming back, the next thing which we can find is basically from the slew rate. We defined the slew rate, we discussed in detail, and the slew rate for this two-stage amplifier came out to be I5 by CC. I5 is the current moving through the M5, so divided by the compensation capacitor. Now the slew rate is provided to us. CC we calculated above, so we can find I5. That was also one of the design parameter which we need for designing or to meeting the specification. So the I5 is equal to slew rate times the compensation capacitor. So it's going to be 20 volt per microsecond multiplied by 5 picofarad, and we end up in the current of a 100 microamps. So that's another parameter which we found. So if we want to put it, this I5 is equal to 100 microamps. If we find this I5 as 100 microamps, we can say this current moving from here is 50 microamps, and this current from here is basically also 50 microamps. So we have 50 microamp flowing from here and 50 microamp flowing from this side. Rather, we just sign should be basically in the opposite direction. So current is going to be downside. So this current is 50, this current is 50, this current is 100 microamps. So we know all this information. And then we concluded in the last lecture that, okay, now we need to do the sizing of M1 and M2, then M3 and M4, and then M5. So for the sizing of M1 and M2, we mentioned that the gain bandwidth product is going to basically help us in finding these values. How? Let's see that thing. So we just see that stuff that we need to find omega 1 over L1 and omega 2 over L1, and we will use the gain bandwidth, which is omega naught. We know the expression of omega naught, so we can find GM1 from that expression. GM1 or GM2, same thing. So if we want to put it, omega naught is equal to gm1 by cc. Again, the cc which we already find out, we will use this value of cc to find the gm1. Omega naught is provided to us, which is 30 megahertz into 2 pi. Because the frequency is given to us, we can convert into radians by multiplied by 2 pi. So gm1 will be f naught into 2 pi into cc. So f naught was 30 megahertz multiplied by 2 pi multiplied by 5 picofarad, which we already calculated. So we will have a GM1 value of 9.4 exponential minus 4. So if we use this value, how we can find now the W1 over L1, which will be equal to W2 over L2. So that's something. Let's see. If we go for the current equation, since we want an amplifier, we want all the time the current equation to be in saturation. We are ignoring the channel length modulation since we are doing an approximate design, and then we are going to place that in the simulation to have an accurate value. So for the ID, if we want to write an equation, it's going to be half mu naught cox W by L times VGS minus VT whole square. So we are interested mainly in finding W by L, which is something which we want. ID, we know this is equal to 50 microamps or 1 by 2 of I5. Mu naught cox should be provided to us because it's technology parameter. So since we mentioned last time we are using 180 nanometers, so mu naught cox which we are going to use is 300 microamps per watt square. This is the mu and cox we are going to use, but we don't know at this moment VGS. Threshold again, we know if we want VTN, we again going to be provided by the foundry, so we can use it as a 0.49. But we don't know VGS. So since we don't know VGS, we need to find another way, because in this equation there are two unknowns and we cannot place the value to find W by L. But we know that we know GM, and how can we use GM? If we see, the GM expression is basically delta ID by delta VGS, which will result into mu n cox W by L VGS minus VT. And if we take the square, GM square is going to be mu n cox W by L whole square VGS minus VT whole square. If we multiply and divide by a factor of 2, then what's going to be this mu naught cox times VGS minus VT whole square by 2 is same thing as ID. So why not to replace this ID, and we will be left with GM square mu naught cox W by L times 2 times ID. And in this equation, ID is known, we just find out in the previous step. GM is known, we just find out now. Mu and cox is provided to us, so we can safely find W by L, and which is the desired stuff. So let's place in and find out the W by L. So if we just do the math, place in the values, the W by L expression will be GM square time divided by 2 mu and cox ID. As we mentioned, mu and cox is provided to us by the foundry all the time, and it's going to be dependent on the foundry process you are using. So for 180 nanometer, we are using 300 microamps per watt square. And if we plug in the numbers, we are going to have a WL ratio of 29.5. So safely we can use a higher number, so we ensure the transistors will remain in saturation. So we are having a W by L for both 1 and 2 of 30. So later on we can just place L as equal to 500 nanometer, and we can find our W. Okay, so we can just find the desired value of W from here. Length of 500 nanometer for 180 nanometer design is a reasonable value. During the simulation process, if we feel we need to increase, we need to play, we can play around, but as a design approximation step, this is a good start. Since we also find another design parameter, so we can plug it back here. So we find the W by L here, W by L here is equal to 30. Same will be here. So we have W by L here equal to 30. So this is 2 and this one is 1. So W by L1 and W by L2, we found the ratio as 30. So now what we need to find? We need to find these two, M3 and M4. So also we mentioned these M3 and M4 are going to be determined by ICM positive. Input common mode range positive. Input common mode range, not common mode range, rather input common mode maximum value. So it is a positive value for us. So for M3 and M4, we will use ICM positive. How we are going to determine this stuff? If we just draw only the, since a differential pair, I'm only drawing one part, which is M1 in series with M3, and M3 is diode connected. Since it's diode connected, M3 will be all the time remaining in saturation, and we need basically both M1 and M2 or all transistors to remain in saturation. But the ICM positive, the main purpose is that maximum value to ensure that at that value both M1 and M3 are going to be in saturation. As we mentioned, M3 is a diode connected. We are not worried about M3. Despite any value applied on V in, M3 will remain in saturation. So we have to take care what's going to be the behavior of M1 with variation of this ICM. So we will put the saturation equation. The saturation equation is that VDS1 should be greater than VGS1 minus V threshold N. So this is V threshold N. So VDS1 safely we can say, if we just instead of comparing with source, we say okay, this is a Vx and this is a VGS, because both Vx and VGS and VDS are comparing to the source point. So we can safely write as Vx should be greater than V in, which is a VG minus V threshold. Now Vx should be greater than equal to some value which is V in. So for the, in order for the saturation, we are placing a DC value, and the maximum value which we are placing is ICM plus. So we are replacing this with ICM plus minus V threshold, which comes out to be Vx should be greater than equal to 1.6 minus V threshold N is provided to us by the foundry as 0.49 volts. So we are using this one. So Vx should be at least greater or equal to 1.1 volt to ensure M1 remains in saturation. If Vx is less than 1.1 volt, this means it's not in saturation. So that is the condition which we find out. So now we know the size of M1, but we don't know the size of M3. We will use this value of Vx as 1.1 volt to find the size of M3. How? If you just see, this Vx point will be equal to VDD, this point is VDD, minus VSG3. So it's a PMOS, so VDD minus VSG3 is equal to Vx. Why? Because gate and drain is connected, so VSG3 will be equal to VSD3. So VDD minus VSD3 will be again equal to Vx, and that's what we want. So we can find safely the value of VSG3. If we can find the value of VSG3, we know the current, we know the VSG, we know the mu and Cux, we can safely find the width and length of M3. So let's do this thing. So coming back to the point, VSG3 is equal to VDD minus Vx. Vx we find out maximum value of 1.11 we can apply. We are designing for the worst case. If we want, we can dilute the values as a designer, but at this moment we are getting one set of value and then later on we can tweak them. So VSG3 is going to be 0.69 volts. So we will use this 0.69 volts in a current equation, which is 1 over 2 mu PUCX, since it's a PMOS, WL by W over L by W over L for 3, and VSG3 minus VTP whole square. So the thing which we need is basically mu P COX, which is again provided to us by the foundry at 60 microamps per volt square. VTP is provided by the foundry as 0.51 volt, 0.51, VSG is 0.69, and ID, which current moving through this node, is 50 microamps, which we figured it out in the previous step. So we can safely find W over L for 3 and 4, M3 and M4, which is going to be 2 times ID divided by mu p CUX VGS VSG minus VTP whole square, so it's a mod value. So if we just do the math, put the values, it comes out to be the width and length of 3 and 4 is going to be around 51.44. So we can safely take 52 value for the ratio of 3 and 4. So that's another thing which we found out, which was required by us. So this one W over L 3 and 4, let's write together, is equal to 52. So we just find a value of 52 for both of them. Right, like separate also, W over L equal to 52 for both 3 and 4. Another thing, now we found M1, M2, M3, M4. Current is here available. Now the left is M5 in the first stage. So M5 is going to be basically determined by ICM negative. How? Let's see. So now we need to find the width and length of M5. So we will use an ICM minus, meaning input common mode value negative. So let's draw again the transistor model for the single end. So just to clarify, this is M1, the current flowing through this node is going to be 50 microamps, but this is M5 and the current moving from here is 100 microamps. It's not like the current is going because there's a branch, another one which I'm not drawing here. So there's another branch here which you can just safely draw like this. But I am not drawing that branch, so because we don't need at this moment. So, and again, we know the V in, we already in M1, we already ensure in saturation, but we don't know about M5. So we need to make M5 in saturation. So for M5 in saturation, if we see this point Vy, Vy is basically a potential applied at the drain of M5 or at the source of M1. And this potential is going to be also the VD sat or the overdrive voltage. The minimum voltage VDS required to ensure the transistor in weak threshold or a sub threshold or a weak inversion is going to be VD sat. So if we just ensure a minimum potential here, or if you find this potential here, we can plug it in the current equation. We know the current here, we know the mu and COX, we know the value of this overdrive voltage. We can safely find again the W by L. So if we just need to find this point Vy, and this Vy we can find from this point V in minus VGS1. So if you see V in, it will be equal to VGS, this potential, plus Vy. And which value of V in we should use? The minimum value which we are applying, since we are talking about the VD sat. VD sat kya cheez hai? The minimum amount of value which need to be applied across M5 so that it remains in saturation. So from V in we should pick the minimum value. So minimum value of VCM V in ki kya hai? That is equal to ICM negative. So we'll use ICM negative equal to VGS1 plus Vy. This is the capital Vy. So let's write a capital Vy. So the capital Vy, which is a VD sat for M5, will be equal to ICM minus VGS1. ICM negative is known to us, provided by the design specification, is a 0.8 volts minus VGS1. So that's something which we need to find. Now VGS1 kya hoga? It's from the M1. We know the width and length of M1. We know the current flowing through M1. So we can safely find from the current equation. So if we just do the math, the VGS minus VT whole square will be equal to 2 times ID W by L mu and COX. We know mu and COX. We know ID1, which is a 50 microamps. If we plug in the numbers, VGS1 is going to be 0.595. We can just plug this 0.595 in this above equation and we can find VD sat 5. So the VD sat 5, if we plug it in the above equation, is going to be 0.2045. Now we have this 0.2045, which is the overdrive voltage, the minimum potential required. So we can plug in this equation of the current, which is ID half mu and COX W by L V overdrive whole square. So again, ID is known, mu and COX is known, W by L 5 is known, and V overdrive is known. Important thing here, ID is 100 microamps because this is I5. In I1 and I2, the current was 50 microamps. So we just plug in the numbers, we find out that or width and length should be 15.92. So we can have a safe side of 16 value. We want a like a not unrealistic value. We need to have a practical value, so it should be an integer number. So we selected W by L of a 5, and one more thing, the W of L of 8 should also be W of L of M8 should also be the same. Why? Let's see in the diagram. So we just mentioned that, okay, we find out the value of W by L of this one is equal to 16. 16, yeah, it came out to be 6. Now, what is the purpose of this one, M8? It's going to provide the current to this M5. And what is the current we need for M5? It as a designer, it's up to me. So but I need to make sure, okay, it should supply this current. So if I make this IREF as 100 microamps current source में ले लूँ 100 microamps का, then this means the ratio between M8 and M5 should be the 1:1, or the size of W over L should be equal to 60. In this way, 100 microamps is going to be supplied to I5. So I designed now the complete first stage, including the current mirror. I have done the sizing of the first stage. Now we need to do the second stage. Second stage is relatively going to be easy. Why? Let's see that thing. So for the second stage, if we just want to see, we did one assumption, or we did in the start, that GM1, this is M1, and GM6, they are almost equal. So if they are equal, we can use the same expression which we have used previously about related to, if you remember, when we know the value of GM, we can find the width and length without knowing the VGS minus VT. But one thing we need to know, ID. And at this moment, we don't know what is the current flowing through this node. I6, yeah, I6 me, I7 me. We don't know the current flowing through his. It's unknown to us at this moment. Okay, we don't know. But we can find. How we can find? From the power value. The power specifications are provided to us, which is 300 microvolts. So we can convert this power into the current. So the current is going to be equivalent 166.66 microamps, and this current should be distributed between the first and the second stage. We already concluded the first stage is consuming 100 microamps, so the current left for the second stage is 66 microamps. So we can utilize 60 microamps on a safer side, because we should be less than this number. So 60 microamps should be utilized in the second stage, or we can safely write or we can safely write 60 microamps is going to be utilized by this node. So the current I6 will be equal to 60 microamps. Just make sure you all are clear about thing. We just have the power number. Power is 300 microwatts. We can find the total current here, which is equal to 300 microamps divided by supply voltage, which is should be equal to 166.6 microamps. 100 microamps is flowing through the first branch. 60 microamps or 66 microamps in reality will be flowing from the second branch, but we are taking 60 microamps to ensure the design specifications are met. So we are using a 60 microamps here. Now when we know the current flowing through this point, we know the value of GM, we can easily find the width and the length ratio of M6. How we can find it? We can just use the current equation again. ID6 this time is equal to half mu P COX VG. It should be VSG minus VT whole square times W by L over 6. We take again the square, GM square, GM6 square, omega L mu P COX 2 times ID6. We can find omega W by L6 by GM6 square divided by 2 times mu P CX times ID6. Now GM6 is equal to GM1, which we concluded as 9.4 exponential minus 4. Mu P COX was 60 microamps per volt square, and ID6 we just assumed and derived is equal to 60 microamps. We plug in the number, omega W by L6 will be 123.2. We can write safely use 124 as a ratio for omega by L. So we also find now omega by omega WL for M6, which is equal to 120. So now the only left transistor for the design is M7, and if you just observe, it's also very much simple. Why? Because we know the current flowing through this transistor is 60 microamps, and its current is going provided by this M8. So it's a current mirror. So this is supplying 100 microamps. We know this width. We can easily find the width length ratio of M7. So it's going to be in reality W7L7 ratio will be equal to 60 times 100. Since this IRAF is 100 micrograms, it's need to apply 60. So it's going to be W8 over L8. ठीक, so हम लोग अगर इसका लिखना चाहें, this value will be equivalent to 9 point something, so it's going to be ratio will be 10. जो इसका ratio आ जाएगा W7 WL7 का, that will be equal to 10. Yeah, so we can use this value as 10. So now we have derived the value of all the transistors. So if you just want to see that, okay, we have figured it out, values of all the transistors which were used in the two-stage amplifier, and that's what the design we want to do. And that is a normal process to do any design. Now we know the ratio of W by L, so we can choose any value of length which is a reasonable based on our requirement. So we can choose a 500 nanometer, and you can find all W's whatever required. You can place them, do simulation, and try to see whether you are meeting the exact specifications or not. Might be you will not meet, but you will reach near to that. But since you reach near to those points, you can just tweak the length and width reasonably. Now you know what is the effect of each and every transistor. If you are not meeting the gain, you know which one transistor size you have to increase or decrease to ensure you meet the requirement to reach the gain. If you're not meeting the phase margin, you can see what you need to do, and vice versa. One thing we didn't insert at this moment was the compensation resistor. If you want to add the compensation resistor, you can add it, and you can just tweak the things accordingly. But this is the normal design process. You have any amplifier, if not a two-stage, if you have any different types, you can do the same thing based on these the provided specifications. The provided specifications will be similar in all designs. So if you have any curious question, you can ask in the next lecture on Monday, or you can also email. We can have a separate session for that point. On the Monday session, Dr. Vala will conduct, or she will just have a video recorded for the simulation setup for the LT SPI, so that you can simulate the same uh, 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 two-stage amplifier based on the values we calculated today, and see how you can have again gain bandwidth, gain, phase margin, feeling, and are you meeting the requirements or no. So I guess we will just close our session, and if you have any queries, you can just send an email, or you can request for a separate session. We can also do a separate session if needed for any Q&A. Thank you, and be safe.